Greetings and welcome to the complete lecture for Chapter 13 of Chemistry 223. And in this chapter, we're going to look at the concept of equilibrium. Most of the time in Chem 221 and Chem 222, we assumed that all reactions went exclusively from reactants to products, and that was kind of the end of the story. However, in this chapter, we're going to see that a lot of reactions, once the products are made, they reform the reactants, and the reactants then make more products, etc., etc. It goes back and forth like that over and over and over again. So equilibrium is an exciting concept, and we'll look at it in this chapter. Should be pretty cool. All right, let's get into the material. So again, most of the time, up till this point, all of our reactions have been reactants on the left, products on the right. But we're going to look at a reaction now in a little bit more detail because there are many reactions which are reversible. And reversible reactions will go left to right as well as right to left. And eventually, the speed of left going to right equals the speed of the chemicals going right to left. And that's going to get us to equilibrium. So it's pretty cool. And at equilibrium, the relative amounts of reactants and products will be approximately the same, all right? There'll be different values, like sometimes you'll have more products, sometimes you'll have more reactants, stuff like that, depending on the nature of the chemical reaction you're looking at. But the overall reactant and product ratio will be about the same. So for chemists to understand this and to talk about it with each other, we use a different kind of arrow. It's called the double-sided arrow. It has different meanings, but as you can see from the examples there, it's like two little arrows, and you can draw two complete arrows or just like half of a left and half of a right, whatever. Sometimes they're called the bidirectional arrow. They're all the same thing. And if you see that, then that means that you have a system at equilibrium.
If a solution of lead ions is added to a solution of chloride ions, a precipitate of lead chloride forms. The equation for the reaction looks typical. If the sample is heated, the solid lead chloride goes back into solution. The reverse reaction takes place. This is an example of a reversible reaction. In the equation for such a reversible reaction, we use a bidirectional arrow.
Temperature affects equilibrium, as we'll see quite a bit. And in this reaction, they made some lead chloride, just probably at room temperature, and then they heated the solid lead chloride until it dissolved, until it formed the ions again. And temperature will absolutely have a huge effect on equilibrium. So this is just an example of the kind of reactions we'll see, and there's lots and lots of uses for chemists, as we'll see in the next several sections. So in an equilibrium, you have to have an equilibrium system which is dynamic. And what that means is reactants will form products, products will form reactants, and they go back and forth. Like they never really stop. You don't get to the point where you have products staying as products or reactants staying as reactants. They go back and forth and back and forth and back and forth. And because they can go back and forth, they're reversible. So that means you can think about them as reactants on the left, products on the right, or really, if you're clever, you can think about it as reactants on the right and products on the left. So you can approach these reactions from either direction. Now, traditionally, chemists have reactants on the left and products on the right, and honestly, that's what I do most of the time. But if you think about it long enough, you can do it both ways. Here's an example of a reaction with a cobalt-2 complex, and the colors are pretty fascinating. I've always liked colors. This is just another example of it. But anyway, in this example, there's a pink version of the cobalt compound, which has 6 waters and 2 chlorines, and you can see that there on the reactant side. And if you heat the pink compound up, it turns into a blue compound, which you can see in that picture. And what's happening is some of the waters have been replaced by chlorines, and the waters are kicked out. This is a reaction which is very temperature dependent because if you take the blue compound and you cool it down, then the waters kind of attach themselves again and kick some of the chlorines out. You end up with the pink COH2O6Cl2 compound, as you can see in the picture. So this is an example of a reaction which is very dynamic. It's very temperature dependent, but you can go back and forth. You can think about the pink reactant going to the blue product, and also think about the blue reactant going to the pink product. And this is an example of how equilibrium systems are so important when it comes to chemistry.
At room temperature, a solution of cobalt chloride is pink in color. When we heat it, it gradually turns blue. If we then cool the solution in an ice bath, it turns pink again. The reaction reverses.
So there are lots of ways to affect the equilibrium. And again, temperature will be a big player when it comes to affecting equilibrium. But there are other ways too that we'll talk about.
When a solution of iron 3 nitrate is added to a solution of sodium thiocyanate, the red-orange iron thiocyanate complex ion is formed. Although the reaction looks complete, substantial amounts of iron ion and thiocyanate ion remain unreacted in solution. When iron 3 ions contact thiocyanate ions in solution, they can react to form a complex ion, iron thiocyanate. As the reaction proceeds, product molecules can react in the reverse direction to separate and reform the original ions. Eventually, the concentrations of products and reactants become constant. At this point, the rates of the forward and reverse reactions are equal, and the system is in a state of dynamic equilibrium.
This is a reaction we're going to look at a lot in Chem 223. This is an equilibrium between iron 3 plus and thiocyanide. They call it thiocyanate, but I call it thiocyanide, same thing. Anyway, it makes the FeSCN2 plus complex ion, and this is an equilibrium. Now, the interesting thing about this is that the iron 3 plus as iron 3 plus as iron 3 nitrate, and the thiocyanide, which is probably potassium thiocyanide, sometimes sodium. Anyway, both of those chemicals in solution are colorless. They look almost clear. The iron might have a little bit of a yellow tinge, but overall they're pretty clear. But when you mix them together to make that FeSCN2 plus complex ion, goodness, you get at least an orange kind of a color there, kind of a burnt orange, I guess. And if you really increase the concentrations, you can make kind of a blood red looking color, which is really cool. But anyway, the important thing here is not my interest in the colors. Sorry about that. But anyway, we're going from a colorless set of compounds to something with a color. And you can see in that beaker, in that picture in the lower left, that you definitely have a color. That's the FeSCN2+. And it looks like the reaction has just stopped. But in reality, what's happening, it's kind of like a dance. And the iron will dance with the SCN-, but after a while, the SCN- goes away and iron starts dancing with water. And then the water goes away and it starts dancing with SCN-. So that's the dynamic part. It's constantly going back and forth, back and forth, back and forth. So you do have to wait in equilibrium for a little bit of time to elapse to get to the point of equilibrium. Honestly, it's not usually too long of a wait for the kind of things we're going to look at anyway. And at that point, the forward and reverse reactions will continue even after the equilibrium is obtained. And we don't see it with our macroscopic eyes, but it is happening. There's lots of examples of these kind of equilibriums, and ice melting to liquid water and liquid water refreezing to ice. That's a great example of one of these equilibriums, and you can see them going back and forth and back and forth. So we're going to talk a lot more about this equilibrium and how we can use it to understand the chemical systems that we observe. For any kind of general reaction where capital A and capital B are making capital C and capital D, and the little a, little b, little c, little d, those are the coefficients, the stoichiometric coefficients for the chemicals. Anyway, for any reaction like that, you can write what's called an equilibrium constant, and it gets the symbol capital K. And K is always equal to the products divided by the reactants. And all the products and reactants are raised to their stoichiometric power. So you can see there for the equilibrium constant K, on the top part there you have capital C in square brackets, that means moles per liter, and it's being raised to the C power, little c. Capital D in square brackets, that's the moles per liter of compound D, it's being raised to the D order there. And then in the denominator, the bottom, you have capital A to the little a power, capital B to the little b power. That's how equilibrium constant works. So an equilibrium constant is going to be nothing more than a number, all right? And the number will actually have a lot of information that we can use to describe the equilibrium. K values are always positive, they're never zero, and they're never negative. K is independent of your starting amounts, so you can have any amounts that you start with and it will still work. However, K is temperature dependent. And the magnitude of K, how big it is, will help us to understand the extent of the reaction. Like, do you have just a little bit of products or a lot of products? And if you do know K, there's lots of stuff you can do. You can predict the concentrations of products and reactants, reactants, and all kinds of other stuff. So we're going to explore in this section how to figure out what K can be. So here's a question you might see. It says, which of the following is the correct form of the equilibrium constant for the given reaction? And you can see in this reaction, we have two SO3s in equilibrium, double-sided arrows, with two SO2 sulfur dioxides and an oxygen, O2. And there's different versions of K. Okay, so the punchline here is that K has to be products over reactants. And the products here are SO2 and O2, and the reactants are SO3. So you can see, for example, like in question A, you do have the products, SO2 and O2 in the numerator and SO3 in the denominator. So that's at least that part of it. However, the one part that A is missing is you have to raise each of the chemicals to its stoichiometry. So the SO3 should have a 2 next to it because there's a 2 by the SO3 right there. And also the SO2 should have a 2 next to it because there's a 2 right there. The O2 would be raised to the first power because there's an invisible 1 right there. So anyway, if you look through those long enough, then you'll see that answer B there has the products, SO2 and O2 in the numerator. It has SO3 in the denominator. But in addition, you're raising the SO2 to the second power because there's a stoichiometry of 2, and the SO3 is being raised to the second power 2. So products over reactants, raise all the chemicals to their stoichiometries, good to go. This isn't really anything you have to know. However, I know that some of you are kind of curious about this, so let me spend just a little time and talk about the origin of capital K. And capital K, the equilibrium constant, stems from the rate constants little k from the kinetics chapters. So as an example of how this works, let's take two NO2s going to N2O4, all right? And you could have a rate for the forward reaction, and rates, as we talked about in kinetics, are usually the reactants. Most of the time, if it's an elementary reaction, the stoichiometry and the power are the same. So NO2 is a second order reactant, and we'd have some kind of K sub F representing the rate constant for the forward reaction. And you can do the same thing for the reverse reaction. Now N2O4 has a 1 by it, so it's raised to the first power. It's probably an elementary reactant, and we'll have some kind of K reverse for the reverse reaction. Well, anyway, what you can do if this is at equilibrium, the rates are the same, all right? The forward and the reverse rates will be the same. So you can let KFNO2 squared equal KRN2O4. You can rearrange the expression in order to have products over reactants. So in this case, it would be N2O4 over NO2 squared. KF over KR is just this product, if you will, of two different numbers. So equilibrium constants K are nothing more than basically the rate constants for the forward reaction divided by the rate constants for the reverse reactions. So again, this is nothing you need to know, but big K is related to little k's, all right? And just like we saw little k's are temperature dependent, big K's are temperature dependent. And that's where this all comes from. It is important that you use capital K for equilibrium and small k for rate constants. You don't want to confuse anybody and stuff. But anyway, this is the origin of it. And if you feel like that cat, like what, whatever, I don't know. Anyway, I totally understand. But anyway, there's a relationship between kinetics rate constants and equilibrium constants. As long as you kind of remember that in the back of your mind, you're good to go. The textbook uses Q a lot more than I would, and I just want to talk about it. Q is really used when you're in an experiment and you're not sure if you're at equilibrium, and we'll talk about Q. Most of the time that the textbook uses Q, I would just use K, but there's nothing wrong really with using Q. It's a little awkward. I'll talk more about this later when we talk about Q, but if you see a Q in the textbook, just assume it's a K, all right? I'll talk more about this in a little bit, but if you look at the textbook, that can be a little confusing. This is a reaction where hydrogen, H2, and iodine, I2, are reacting to make two hydrogen monoiodides. And what we see here, if you look carefully, the line that starts in the upper left and kind of goes down to the lower right with H2 and I2, there's both a red line and a blue line, and they're right on top of each other because every 1 mole of H2 is going to need 1 mole of I2, so they're going to have the same behavior. And they're both reactants, so they're both going to be diminishing over time. They're going to go down. Now, on the other hand, HI here is the product. HI is going to be appearing. So that picture, which is the concentration on the y-axis, that picture shows correctly HI getting bigger and bigger and bigger. But finally, you get to some point where the relative amounts of HI and H2 and I2 are about the same. And that's where chemists consider equilibrium to have been achieved. If you pick a point to the right of the red line I just drew there, that's going to be equilibrium. If you did it to the left, you wouldn't be at equilibrium yet. Like your HI wouldn't be big enough and your H2 and I2 would be too big. But this is what chemists are thinking about when they say it gets to a kind of a constant rate. You want the HI amount to be relatively the same, and you want the H2 and the I2 amount to be approximately the same. So in the equilibrium region, when you want to write an equilibrium constant, that equals products over reactants. There's a 2 in front of the HI, so we would write HI squared divided by H2 and I2. And again, the square brackets means moles per liter. Now, the value of this equilibrium constant has been studied quite a bit, actually, and the value is 55.3. So big K is usually a unitless quantity. You can put units on there if you want to, but it's honestly kind of tedious and not very helpful. So scientists usually just report the value of K, not anything. Remember, K can never be negative or 0, but it can be anything larger than 0. This is 55.3. In this reaction, we're taking a compound that's NaOCl, nitrogen oxychloride. We're placing the nitrogen oxychloride in 2 moles of it in a liter flask. And at equilibrium, we find that once everything settles, we end up with 0.66 moles per liter of nitrogen monoxide, one of the products. We can actually use this information to calculate the value of K. So if you need to find the value of K, almost always you'll set up what's called an ICE table. ICE is an acronym, but to build the ICE table, you want to have reactants and products. So you can see right there, I've got NaOCl and then NO and Cl2. And sometimes if you want, you can even put the stoichiometries next to them. Just kind of helps out. So there's a 2 in front of the NaOCl and a 2 in front of the NO. You don't have to do that, which I didn't here, but I'll do it anyway just for the heck of it. ICE stands for initial for I, and initial is literally how much you start with. So in this problem, we had 2 moles in a 1 liter flask, or a molarity of 2.00 molal. That's the initial NaOCl. And we didn't have any NO or Cl2, so they're just empty. Now, C stands for change, and E stands for equilibrium. So you can see what we have here, ICE, initial change equilibrium. Equilibrium is going to be important, and the other piece of data we have on this reaction is the 0.66 moles per liter of NO. So right now, we're missing quite a few values, but this gives us a good chance to talk about what ICE is all about. First of all, it's the equilibrium lines, the equilibrium concentrations that we will use to calculate K. So once we know all those values, we'll take NO squared times Cl2 and divide by NoCl squared, and that'll allow us to find K. But we're not quite there yet, as you can see, because we're missing some points. Now, the change of the reaction shows how much the NO in the middle column goes between the initial point and the ending or equilibrium point. And you can probably see that NO is increasing by 0.66 moles per liter. Remember, there was nothing to begin with, and at the end we had 0.66 moles per liter, so NO changed by 0.66 moles per liter. Now, earlier I said the stoichiometries can be helpful, and this is one place where it can be super helpful, because we can easily calculate how many moles per liter of chlorine were also created. And we do that because 2 moles of NO are created for every invisible 1 mole of chlorine. You can see it better up here in the balance reaction, 2 NOs for every 1 Cl2. So you could write 0.66 moles NO per liter. You could then have 2 moles of NO on the bottom and 1 mole of Cl2 on the top. Kind of like a grams, moles, grams thing, but just the moles to moles part. But hopefully you can see that if 2 moles of NO are created, that means 0.33 moles per liter of chlorine were created. So notice here that there's a 2-to-1 ratio in the formula, and the concentration of NO is twice as much as the concentration of Cl2. They're going to be made at the same time. There's a 2-to-1 ratio. That's where that came from. So at equilibrium, the amount of Cl2, 0.33 moles per liter. But we're not done yet, because the NO and the Cl2 had to come from something, and they're coming from the NOCl. So again, notice how there's 2 NOCls being used up for every 2 NOs that are being made. Well, if NO and Cl2 are increasing, their products, they're being made, they have to come from something, and they're going to come from the NOCl. So if there's a 2-to-2 ratio of NO to NOCl, and NO is being made, that means the NOCl has to go down by 0.66 moles per liter. So NOCl is going to be going down by 0.66, while NO is going to increase by 0.66, and Cl2 is going to increase by 0.33. And I want you to stop just for a second and look at that change table, because there's a 2-to-2-to-1 ratio in that change line, similar to the 2-to-2-to-1 ratio you see up here in the balanced reaction. So the change line is very susceptible to stoichiometry. We had a 2-to-2-to-1 ratio in the balanced reaction, and in the change line you can see we have 2-to-2-to-1. It's 0.66, 0.66, 0.33, but same idea. But the other thing is that notice how the reactant is decreasing. It's going to have a negative value because that's the part that has to be used up in order to make the NO and the Cl2. So that's kind of cool too. Now, to finish this table off, the NOCl at equilibrium will be the initial amount minus the change part. That's going to be 1.34 moles per liter when you do the math. So initial, and then use the change to figure out what the equilibrium is, you're good to go. So at equilibrium, in the next slide, we're going to use this line right here, the equilibrium values, to calculate K. It'll be the products over reactants. We'll raise the NO and the NOCl by 2, because that's what their stoichiometry is, and we'll plug those numbers in to calculate K. But at the end of the day, just remember, the change line will reflect the stoichiometry perfectly. And since we have a 2-to-2-to-1 ratio in the balanced formula, that is reflected in the numbers, like absolute value, all those numbers, 0.66 to 0.66 to 0.33, that's 2-to-2-to-1. However, reactants will go down. In this case, that's why there's a minus 0.66 under NOCl, and the products will both appear, positive 0.66 and positive 0.33 respectively. So here's the non-messy version, if you will, of that ICE table. Much better handwriting than I can use, but hopefully you get the idea. Again, I want you to focus on big time the importance of the change level. The change line there reflects stoichiometry. So 2-to-2-to-1 and NOCl to NO to Cl2 in the balanced reaction is reflected here, 0.66 to 0.66 to 0.33. That's 2-to-2-to-1. There is also, if you will, a line of demarcation between reactants and products. And so in this case, the reactant is going down and the products are going up. And this will always be the case too. Like products will be up and reactants will be down, or you can have it reversed like we'll see, i.e. sometimes products will go up and reactants will go down. But anyway, it's always going to be this line, and on one side everything is positive and on the other side everything is negative. So now that we have the equilibrium concentrations of all reactants and products, we're going to use that E part of the ICE table to actually calculate the value of K. And K is going to be products over reactants. It's going to be the NO quantity squared, because of the 2 in front of the NO, times Cl2 divided by NOCl squared. Again, that squared also comes from the 2 in front of the NOCl. So you literally plug those values in, 0.66 squared times 0.33 divided by 1.34 squared. Bam! 0.080 is your equilibrium constant. So pat yourselves on the back. You just calculated your first K. Can your heart stand the strain? When you're writing equilibrium expressions, you do not want to include solids or liquids, and that's really important. So basically, in an equilibrium constant K, you will only write gases and aqueous solutions. So for this reaction, sulfur and oxygen making sulfur dioxide, notice the sulfur is a solid, so you'll leave that out. This K would be just the SO2 divided by the O2. For water, that's going to be the number one reactant that we will not include in equilibrium constants quite often. So in this reaction, which is ammonia and water making ammonium and hydroxide, your K value would be ammonium times hydroxide divided by NH3, but you won't put the water in. And this is a good time just to remind you that NH3 is ammonia, NH4 plus is ammonium, and they're quite different. The reason for the solids and liquids not being placed in is often referred to the fact that solids and liquids have an appreciable density. And if you change the concentration, it's like changing the grams over volume, which is basically molarity, which is basically density. All right. And so that's why they feel that there's no real appreciable change for solids and liquids. I don't care if you believe it or not. I'm not even sure I believe it sometimes. But the important part, once again, no solids and liquids in equilibrium constant expressions. So here's a reaction. We have potassium metal. Potassium is a solid, K solid, reacting with water to make KOH and H2, and you want to have the appropriate equilibrium constant expression. Well, the big punchline here, of course, is that you don't want to put solids and liquids in your equilibrium expressions, but aqueous parts and gases are okay. So if you look at this, the K is a solid, so that's not included. Water is a liquid, that's not included. So notice that everything on the reactant side is not going to be part of the equilibrium expression. So if you run into this, just think of that as a big 1, all right? It's not like you don't have it, but it's just that nothing shows up. So in this problem, the products will be KOH squared times H2, and that's okay. And in the denominator, everything cancels out, so you would just put a big 1 or an invisible 1. And that means answer E will be the correct version, all right? So if everything is a solid and liquid, just put a 1 right there. It's no problem, but you still have to include the KOH and the H2. There's more you can do with equilibrium constants. This is sulfur plus oxygen making sulfur dioxide. Let's call the equilibrium constant for this one K1. It would equal SO2 divided by O2, but again, don't put the liquids, or in this case solids, in the equilibrium expression. However, let's say that you wanted to add 1/2 more oxygen, and you wanted to make sulfur trioxide instead of sulfur dioxide. All right, no problem. K2, products divided by reactants. So for K2, the second expression, it would be SO3 divided by SO2 times O2 to the 1/2 power. So raising the stoichiometry in this case gives a raise to the 1/2 power. That's like taking the square root of the O2, by the way. Well, let's say that your instructor came around and said, why don't you just figure out an overall K for all of this, i.e. what would be the equilibrium constant for sulfur reacting with 3/2 O2 making sulfur trioxide. So the sulfur dioxide, which was a product in the first one, and the sulfur dioxide, a reactant in the second one, are essentially canceled out. Well, the overall K then for this reaction would just be sulfur trioxide divided by O2 to the 3/2 power, and when you do the math, it's actually equal to K1 times K2, because again, the SO2s will cancel out. In K1, it's a numerator SO2, and in K2, it's a denominator SO2. And the O2 and the O2 1/2 combine to make O2 3/2, the joys of these exponents, so you end up with sulfur trioxide divided by O2 to the 3/2 power. Your instructor says, hey, fractions are lame, get rid of them, multiply everything through by 2. So you've got the old K, which is sulfur trioxide divided by oxygen to the 3/2 power, but your instructor is being mean, I guess, so instructor says multiply everything through by 2. Okay, no problem, so do it. So the new K is going to be SO3 squared, because now there's this 2, and it'll be O2 to the 3rd power. However, if you look at this one long enough, the old old K, if you would square it, that's going to give you the new K. So SO3 squared would give you SO3 squared, which is what we see. And the O2 3/2 in the denominator squared, the 2's will cancel out. You'll end up with O2 3. So if you multiply a reaction through by 2, you raise the K value by the same number. So if you had to multiply a reaction through by 3, you would take the old K and take it to the third power in order to find the value of the new K. Kind of a handy little trick there. If you change direction, sulfur and oxygen making sulfur dioxide, and then decide to change it to sulfur dioxide making sulfur and oxygen, you can absolutely do that. Remember that these are reactants going to products and products going to reactants. Well, if you compare the old K to the new K, they're essentially the reverse of each other, all right? So the old K had oxygen in the denominator, and now in the new K, oxygen is in the numerator. So if you flip a reaction, you take the inverse of your old K. So 1 over the old K equals the new K when you reverse it. It's pretty chill. There's a handout down there called Manipulating Equilibrium Constant Expressions. I encourage you to check it out for more details as to how this works. But these are things that can just make your life a little bit easier. Here's a reaction where N-butane is in equilibrium with isobutane. And these are organic molecules. We'll talk about them at the end of the term. But the equilibrium constant K equals 2.5. So the question, what's the value for the reverse reaction, which would be isobutane as a reactant going to N-butane? Well, to get the value of the new K, you would take the inverse of the old K. So since these reactions are literally flipped, the new K will be 1 over the old K, 1 divided by 2.5. And if you throw this in your calculator, 1 divided by 2.5 is 0.40. That's going to be the value of your new equilibrium constant. Now, all the K's we've written so far are called K sub C, and K sub C is by far the most common equilibrium constant. The little c there stands for concentration, and concentration in chemistry is almost always moles per liter, the big M. However, you can have what's called a K sub P, and KPs are gas equilibrium constants. Now, if you're using a KP, you have to use atmospheres for gases, all right? And 760 millimeters of mercury equals 1 atmosphere, if you remember from Chem 222. So if you're dealing with gases, you can use KP, no problem. Just make sure all your pressures are in atmospheres. So here's an example of a reaction that you could write as a KC or a KP, depends on how you want. All the reactants and products are gases. So a gas can have moles per liter, like in a flask, that's no problem. But you could also have the individual pressures of the gas. So a KC for this reaction would be ammonia squared divided by nitrogen divided by H2 to the third power, and that's totally cool, and that's probably how we'll write it most of the time. However, if you had just a bunch of atmospheric pressure data, Kp would be the pressure of the NH3 squared, and you would divide by the pressure of N2 and the pressure of H2 to the third power. And again, all those pressures have to be in atmospheres. So use the one that's easiest for you. Most of the time, Kc is great, but if you have a Kp, no problem too. If you have a Kp and you need to turn it to Kc or vice versa, you can use this expression right here. Kp equals Kc times RT to the delta N. So T is temperature, the Kelvin temperature of your system. R is the gas constant R, 0.082057 liters atmospheres per mole Kelvin. And then delta N is the change in moles of gas. And you only look at the gas. You don't look at the solids, the liquids. You don't even look at the aqueous parts on this. So delta N, products minus reactants for gas. So for the ammonia example we just did, delta N would be 2 for the products, 2 moles of gas, minus a total of 4 moles of reactants. 1 nitrogen plus 3 hydrogen is 4. So delta N would be 2 minus 4 minus 2. And you could plug that into delta N at that temperature, the gas constant. You can turn your Kc into Kp, no problem. Delta N can be positive and negative. It can be 0 as well, where Kp and Kc are the same. But more often than not, there's a slight difference between Kp and Kc, so that's where this all pops in. So the question here is, what's the delta N value for this reaction? And we have here ammonium sulfide breaking down into ammonia and H2. So delta N is the moles of gas as products minus the moles of gas that are reactants. And you can see here we have 2 NH3 and 1 H2S, so that's 3 moles of gas. But on the reactant side, we don't have any gas, so that would be 0. So for delta N here, it would be 3 minus 0, 3 moles of product gas minus 0 moles of reactant gas. Delta N is going to be 3. The magnitude of K will tell you if you have more products than reactants or if you have more reactants than products. And it's kind of a general kind of rule. It's not super specific. And sometimes I've had huge Ks that didn't really have that much more products than reactants, but it does give you at least a ballpark figure as to what to expect. So if you have a K that's greater than 1, you will have a product-favored reaction. The product dominates at equilibrium. So since you have more product over a reactant, product over reactant will be greater than 1. That's what having a K value greater than 1 is. On the other hand, we're going to see a lot of Ks that are much less than 1. That means you have more reactants around than products. Your reactant will dominate at the equilibrium. So literally, the number you get for K, if you got a K of, say, 70, well, 70 is greater than 1. That means you have a product-favored K. You're going to have more products than reactants. On the other hand, you calculate a K of 0.017. Well, that K is less than 1. That means you'll have more reactants at equilibrium than products. This is an example of a reaction which is very product favored. That K is much, much, much greater than 1. This is how they make ammonia, all right? And it's very product favored, and we know that as chemists because your K, 3.5 times 10 to the 8th, is just huge. It's much, much, much greater than 1. So numbers greater than 1 mean product favored. And so when that equilibrium hits, you're going to have more ammonia, NH3, than you'll have nitrogen and hydrogen. You can have Ks less than 1 too. This is the K for silver chloride breaking up into silver plus and chloride ions. And the equilibrium constant K, products divided by reactants, would be silver plus times chloride divided by 1 because we don't include solids and liquids in the equilibrium. Well, this K is 1.8 times 10 to the minus 5. That's very, very small. So this reaction is reactant favored. So for the silver chloride, we should see more of the white silver chloride solid, then we would see the dissolved ions, if you will. But again, the important part, K is less than 1, reactant favored, K is greater than 1, product favored. These two graphs show the progression of some kind of chemical, and you can see the first one there on the left, the products is quite a bit higher than the reactants. So that means we have more products than we have reactants. That's a product-favored reaction. K should be greater than 1 for that case. On the other hand, the second graph there shows how reactants, when they stabilize, reactant concentrations are higher than products. So in these cases, you're going to have an equilibrium constant less than 1. That's going to be a reactant-favored condition. In this question, we have two equilibria. Two NO2s are in equilibrium with N2O4. K is 180. The second reaction is iron 2 hydroxide as a solid in equilibrium with iron 2 plus and 2 hydroxides. And it wants to say which reaction is true. So the first one says both reactions are product favored. Well, the first one is K of 180 is certainly greater than 1, so that's going to be product favored. But the second one is certainly not. That K is much less than 1. That's very reactant favored. So that's not going to fly. We have one product favored, the first one reactant favored, the second one. So A is out because both reactants are not product favored. B is out because both reactions are not reactant favored. K, the first one, is greater than 1, so it's product favored, but not the second one's reactant favored. So then it says C, reaction A is product favored and reaction B is reactant favored. That sounds good to me. That's like saying K of the first one is greater than 1 and K of the second one is less than 1. That's what we see. Answer C is the correct answer. Now, earlier I said how our textbook likes using Q a lot more than I do. So let's talk about what Q is, at least in the classical sense. Q is really helpful to chemists if you're not sure you're at equilibrium or not. And I think that's why the textbook authors became kind of obsessed with using Q all the time instead of K, because how do you know? And there's something to be said for that. However, in our Chemistry 223 class, Q will be used to kind of compare to a known value of K to see if you're at equilibrium or not. Q is described exactly as K. It's products over reactants, so big C and big D divided by little a and little b, and all of those letters are raised to their stoichiometric coefficients. But here's the thing, it's got the same form as K, so if Q and K are the same number, your system's at equilibrium, and you're good to go. On the other hand, if Q is not the same as K, that means your system is not at equilibrium, and you can make predictions as if you're going to have more product or more reactant. Here's kind of a visual image of how to compare Q and K. So in the middle part there, Q and K are the same value. Q is red and K is blue. And you can see they're the same number. So if Q and K are the same, your reaction's at equilibrium and you're good to go. However, what Q is used mostly for is to see if you are at equilibrium or not. And so you have to have a K value to compare your Q to. And if Q is less than K, it means that Q wants to become more like K. Q's going to have to turn a lot of your reactants into products. So if Q is less than K, we will say that the reaction should shift to the products, to the right-hand side. On the other hand, once in a while, we'll see that Q is a number greater than K. That means usually that you're starting from the product side and the products are breaking down to reactants. But either way, if your Q is greater than K, what that means is you're going to have a shift to the reactant side. You have to turn some of those products into reactants for equilibrium to kick in. That's going to be what happens when Q is greater than K. So notice the right and the left there. Q less than K means it's going to shift to the products, and a shift to the products means a shift to the right, because products are almost always on the right side. That's where we're using it. On the other hand, Q is less than K. That means you're going to have a shift to the reactants. Products are going to have to make reactants. That's called a shift to the left. So right and left are used a lot in chemistry. Right means towards the products. Left means more towards the reactants. So here's an example of how we can use reaction quotient Qs. The important part that I always find is that you can tell if you're at equilibrium or not. So this is the N-butane to isobutane equilibrium we mentioned earlier. And I'm just going to abbreviate isobutane as iso and the N-butane as N. But anyway, this reaction has been studied and its K value established at 2.50. So that means you have more products than reactants because K is greater than 1. Maybe it's not super big, but it's going to be a lot more products, or it's going to be a little bit more, at least, products relative to reactants. So let's say that we're doing this reaction. We measure the chemicals. Iso concentration is 0.35 and the N-butane concentration 0.15. Are we at equilibrium? If we're not at equilibrium, which direction will it shift? Will we have more products being formed and less reactants, or will we have more reactants and less products? This is what I feel a Q is good for. So what we're going to do in this problem is we're going to literally figure out Q. It's going to be product, the isobutane, divided by the reactant, N-butane, and we'll compare that number to the 2.50 established number, and we can from there predict if the reaction will shift to the right or the left. So in this problem, the iso was 0.35 moles per liter and the N-butane was 0.15. Products divided by reactants, there's no weird stoichiometry, etc., etc. Q comes out to be 2.3. Now that's close to, but not the same as 2.50. So in this case, what's going to happen is you're going to end up making more products. The reactants will shift to the product side and more products will happen. So this is how I like to use Q. Like you have an established equilibrium constant and you're trying to confirm if you're actually at that equilibrium or if you're not. Here's a similar kind of question. It's the N-butane isobutane reaction. The K is 2.5, and the N-butane is 0.02, and the isobutane 0.03. And the question says, is this reaction at equilibrium? Well, first of all, if it's at equilibrium, Q and K must be the same. And for this reaction, we have 0.03 divided by 0.02. That comes out to be 1.5. And 1.5 is certainly not the same as the established K value, 2.5. So we are not at equilibrium. Our Q is less than K. And if Q is less than K, you're going to make more products than you are reactants. Another way to say that is a Q value less than 2.50 would imply too much reactants. So this is kind of a cool way to get this around, but when you see this, it's pretty chill. Q is products divided by reactants, 0.03 divided by 0.02. Q comes out to be 1.5. Q is less than K. Reaction is not at equilibrium. Those numbers would be the same if you were at equilibrium. And we're going to shift to the right. You're going to have more products, the isobutane, than you have reactants, the N-butane. Nothing you can't do. So to calculate equilibrium constants and the concentrations that go along with them takes a little bit of practice, I won't lie. So I'm going to try and share with you some of the ideas here that might be helpful. So we're back to the H2 and the I2 making 2HI, and 55.3 is the equilibrium constant. So let's say we put a mole of hydrogen and iodine in a 1 liter flask. How does that work out? Let's calculate the equilibrium concentrations. Well, you guessed it, we need an ICE table, initial change in equilibrium. Initially, we have 1 mole of H2 and 1 mole of I2 in a 1 liter flask. So the concentrations of H2 and I2 are just 1, and HI would be 0. Then we're going to use the stoichiometry to go to the change part. H2 and I2 will go down by x, and HI will go up by 2x. And that's because there's twice as much of HI being made for every H2 and I2. So at equilibrium, you're going to have 1 minus x for H2, because we don't know what x is, we can't go any farther. I2 will also be 1 minus x, and because of the stoichiometry of 2 by HI, that positive 2x will go down as to positive 2. So it's kind of cool. We're going to have one equation and one unknown, nothing you can't handle. So at equilibrium, you have the HI squared divided by the H2 and the I2. Now, we'll talk about H2 and I2 in just a little bit. However, we want to, on the top there, we want to put 2x quantity squared. It's not 2x squared, like 2 times x squared. It's 2x quantity squared. So it's like 2x times 2x. Now, initially, this reaction right here, it has one unknown, x, but there's a lot of pieces to it. We'd have to solve it as a quadratic, stuff like that. However, in chemistry, it's very common to see a reaction like this where you can take the square root of both sides. So bear with me here for just a second. Square root of 2x quantity squared is like square root and squared. They cancel out. It's just 2x. And in the bottom, you have 1 minus x, and if you multiply them together, 1 minus x quantity squared, well, we're square rooting it, so that goes down to just 1 minus x. And then finally, you want to take the square root of 55.3. Your calculator can do this for you. It comes out to be 7.44. At this point, we'll use the distributive property. 7.44 times 1 is 7.44, and 7.44 times minus x is minus 7.44x. And we can then combine all of the x's, because remember, all of that equals 2x. We will add 7.44x to both sides, so we'll have 9.44x. 7.44 plus 2 is 9.44. 9.44x equals 7.44. We can then solve for x by dividing by 9.44 on both sides. That leaves just x. X is going to equal 7.44 divided by 9.44, and that equals 0.788. Now, from this point, you can figure out the H2, the I2, and the H2. The H2 and the I2 are both equal to 1 minus 0.788, and that comes out to be 0.2 0.221 moles per liter. On the other hand, if you're curious, the HI will be 2 times the X. 2 times 0.788 comes out to be 1.58 moles per liter. So these are the values at equilibrium. Here's another kind of reaction. This is dinitrogen tetroxide making nitrogen dioxide with a 1:2 ratio. So the K value, a Kc expression, products divided by reactants, that's going to be NO2 squared divided by N2O4. And this reaction's been studied a lot, so it's 0.0059. So that means this is a very reactant-favored set of conditions, all right? So at the end of the day, we're expecting more reactant than product. So we're starting with 0.50 moles per liter N2O4. What are the equilibrium concentrations then for the N2O4 and the NO2? And this is the kind of question you can absolutely answer. Now, N2O4 is more or less colorless, while NO2 is a very sharp brown. And you can see, like in the pictures in the lower right, the right-hand side one has NO2, and the left-hand side one probably has a lot of N2O4. So it's not really that important for our problem, but it's kind of cool to think about, especially for the stuff coming up. So we'll set up the ice table. Initially, we have 0.50 moles per liter N2O4 and no NO2. And like before, the change part will reflect the stoichiometry. That's a 1:2 ratio. N2O4 will go down by X, NO2 will go up by 2X. So at equilibrium, 0.5 minus X for N2O4, and NO2 will be equal to 2X. We need to square the NO2 because of the stoichiometry. So 0.0059 equals quantity 2x quantity squared divided by 0.50 minus x. And this is a problem you can solve. It uses what's called the quadratic formula. It's a pretty easy kind of program to use, and I will certainly pass that along if you're interested. But we do have one unknown and one equation, so let's see how you can solve it. We're going to solve this Kc. We're going to have to use what's called the quadratic equation to solve it, and here's what I mean by that. So first of all, let's try and clean this up a little bit. We'll multiply both sides by 0.5 minus x, so the 0.5 minus x in the denominator on the right goes away, but then you have 0.0059 times 0.50 minus x, and that's going to equal 2x quantity squared. Well, 2 squared is 4, x squared is x squared, so that comes out to be 4x squared. Now, 0.0059 will multiply by both 0.50 and minus x. So when you look at this long enough then, the 0.0059 is going to be multiplied by 0.5, and that's where this number comes in, 0.0029. But it's also going to be multiplied by minus x. So you can see right there, you've got a minus 0.0059x. It's minus x, so that's where the negative comes from, but this is the idea. And all of that, of course, equals 4x squared. So when you rearrange this, and usually the x squared value is a positive number, by the way. But anyway, the number in front of the x squared is certainly positive when you write it like this. So 4x squared plus 0.0059x minus 0.0029 equals 0. Now, the quadratic formula always looks like this. It's an ax squared plus bx plus c equals 0. And that's what we have here. So in this problem, a equals 4, b is 0.0059, and c is minus 0.0029. The quadratic formula is minus b plus or minus square root b squared minus 4ac over 2a. And that's where those values come from then when you figure them out. So for example, this is what the quadratic formula filled out would look like. You can see you've got the opposite of b plus or minus square root b squared minus 4ac over 2 times some kind of an a factor. So in your calculator, when you solve this, and I'm going to encourage you to do this, at the very end, you're going to get 2 answers. You're going to get 2 answers because of this plus or minus part right here. So when you do this, either manually or in your calculator, as I'll talk about, you end up with x equals 0.026, and you're also going to end up with x equals minus 0.028. But the good thing about chemistry is that because we're all based on moles per liter, like in the ICE table, and moles per liter is based on moles, which is based on grams, you cannot have negative mass in chemistry. There are no negative numbers for mass, moles, molarity, stuff like that, because that's just talking about then turning something positive, a positive mass, into a negative mass, and that doesn't exist, at least in our universe. So for this problem, you don't want anything to do with the negative root. Just ignore it. X is only going to equal positive 0.026 because that's where matter is, always positive numbers. So the N2O4 will be 0.5 minus X. That comes out to be 0.47 moles per liter. And the NO2 will equal 2 times the X, 2 times 0.026, and that'll give you 0.052. So you're good to go. Now, in the 21st century, the solve function on calculators can be really, really helpful. And if your calculator has a solve function, you can make mincemeat of these quadratic formula problems. And I encourage you to check that out if you want. If you do this problem correctly, you should end up with 2 same answers as I do, all right? If you don't see these numbers, of course, let me know. If you use the solve button, though, I want you to report both roots, not just the positive root, but I also want you to report the negative one. And you can say, that's lame, doesn't do anything or whatever, but make sure that you report them both, all right? Not just the answer that I'm looking for, but report both of the roots.